In 1.13, we are removing discontinuities, which means we're trying to make a function continuous. Okay, recall from a previous section that if it's a removable discontinuity, the limit as x approaches c of f of x exists, but the limit as x approaches c of f of x is not equal to f of x, meaning there's some function, and then there's somehow a weird hole in the middle or something. Maybe it's up here. Okay, so example 1, we're going to do it step by step, and then we'll fill in the blanks. Okay, let's look at function f of x. First thing, it says there is a hole in this function. There is a hole in this function. Let's simplify this. The x minus 1's cancel, leaving x plus 1. Because the x minus 1 canceled, there's a hole where x minus 1 is equal to 0. Since x minus 1 can't equal to 0, and x can't equal 1, there is a hole at x equals 1. Now, how do we find the y value of the hole? Okay, because it's not there. I can't plug it in the original function because that'll give me 0 over 0. So I'm going to plug it in this simplified function. So if I plug it in this simplified function, I get 1 plus 1, which is 2. So the y value is 2. Okay, now I'm going to rewrite f of x so that it is continuous for all real numbers. Okay, so I'm going to make it a piecewise defined function. Okay, so I know that before we had it was x squared minus 1 over x minus 1, but I am aware that x can't equal to 1 because there's a hole there. So at x equals 1, what do I want the y value to equal to? Well, I want the y value to equal to 2, so I'm going to put a 2 here. Okay, now I've rewritten the function so that it's now continuous. I'm going to draw a sketch. It's not going to be the real graph, but let's just draw it. Okay, there's this function right here. There's a hole here, an open circle here. So rather than leave the open circle here, this is saying use this function except at x equals 1. At x equals 1, go ahead and fill in the blank with the 2. So I'm closing that dot and making it a continuous function. Let's go ahead and look at example 2. Okay, if the function f is continuous for all real numbers, and if f of x equals x squared plus 6x plus 8 over x plus 4 when x is not equal to negative 4, then what's f of negative 4? Okay, this is saying x can't equal to negative 4. Okay, but it's also telling me that this is a continuous function. So kind of like in part C of the previous step, we have to fill in the blank to figure out what do we want f of negative 4 to equal to so that it will be a continuous function. So I'm going to go ahead and factor and simplify the expression or the function, I should say. Now I can see why x can't equal to 4. Okay, let me cancel out the x plus 4. So I'm going to get x plus 2. Okay, which is going to leave me with this function once I take out the hole. Okay, so I want to remove the hole, so this is continuous. So at f of negative 4, I want this to equal to negative 4 plus 2, which is negative 2. Okay, so again, that's just filling in the hole, and by defining it that way, it's now a continuous function. Okay, example 3 is asking the same thing, it's just asking it in a different way. So it's telling me this is f of x, it's defined this way when x is not equal to 6. Figure out what a has to be so that it at x equals 6 so that it will be continuous. Okay, again, let's simplify the function. Okay, and we can see exactly why this is not continuous at x equals 6. Okay, so if I simplify that, I get x plus 3. Okay, now what do I want to think about? At x equals 6, that would be 6 plus 3, which is 9. So I want this a to equal to 9 to make this a continuous function.